Hello, everyone. I would like to introduce our next speaker. It's Ladislaus. He's a longtime member of the Eastacre community, and today he's going to be talking to us about validating from Hardware Enclaves. Take it away, Ladislaus.
Hey, everyone. Thank you very much for coming. My name is Ladislaus, as Nolan said. Thank you very much. I'm a member of the Eastacre community, and I'm very humbled to be able to speak to you today about validating from hardware enclaves. Please take in mind, I'm everything but a computer security researcher, so take everything what I say here with the appropriate grain of salt. I'm simply reporting back sort of my experiences when tinkering and testing and using those tools we're going to talk about today, and sort of give a high-level overview conceptually also. And it takes about, let's say, 15 minutes, and then I hope we've got some time for questions. So quick recap to get things started. We're talking about validator key protection today. And yeah, of course, to avoid common slashing risks. And validator key protection is not trivial. So I've brought up here this iconic diagram from the fine folks from attestation, basically showing the different layers of protections. For validator keys, not a lot has changed since this has been published. So basically we start at the nucleus, right, with sort of the default of protecting keys, meaning they have to be hot on disk, right? You generate your key store and then have attached to it a passphrase. And then the further out you go, the security layers, if you will, then you sort of reach at some point maybe the separation of concerns between a validator client and your remote signing software, such as Web3 signer by consensus. And even further out, you could sort of add some more cryptographic, advanced cryptographic primitives like DKGs, threshold signing, and basically enter sort of the DVT distributed validator space. But the key here is, right, we usually have like this key hot on disk to show up for consensus duties, right? And sort of what we are going to look at over the next few minutes is sort of this in-between layer, as you could say, where we would try to put a remote signing software inside a hardware enclave. And so sort of the TLDR to sort of make you aware of and what validating from hardware enclaves even means is, think about your generic hardware wallet and which stores your keys, like you generate a key inside this hardware wallet. And basically what we add on top of this is program logic. So we add some smart functionality here, and this is, in our case, slashing protection rules. So what we get is this nice system where we have protection not only at rest, but also at runtime. And sort of also what's nice here is it's really tough, or we get a system where it's really tough to exfiltrate the generated keys inside, but still are able to perform consensus duties from it. Right, as shown here, proposing blocks or testing to them. And so the original idea to do so stems from this ETH research post by Justin Drake, where he basically proposes hardware-based slashing protection for liquid solo validating pools. And just to give you a very brief idea, like what are the properties of hardware enclaves? Like what are we talking about here? So on a very, very high level, like we have to think about hardware enclaves, or the specific hardware enclaves here, as some form of isolated, encrypted areas of our CPU memory, which are supposed to be like untemperable, and sort of we trust the code execution inside it. So what we receive as users is some form of confidentiality and integrity guarantees on the code and on the data running inside those enclaves. And basically the underlying hardware itself sort of ensures that those properties hold. And just to briefly contrast this from multi-party computation systems like DVT in a sense, or more advanced cryptographic primitives, we get this. It enables us to sort of run arbitrary and very inexpensive computation, almost at the native speed of the CPU, which is in the staking context particularly interesting, as sort of latency is a critical component, right? So what I want to introduce today to you is this software called Secure Signer. Secure Signer is this open source validator remote signing tool, adapted to be run inside trusted hardware inside hardware enclaves. It's written in Rust, has been originally funded by an Ethereum Foundation grant, and the Puffer team, Puffer finance team went on to develop this tool. And basically what it is a Web3 signer implementation adapted to be run inside hardware enclave. So simply what it does is sort of you have your hardware enclave, and then you instantiate the enclave with a remote signing program logic running inside it. And what you also store and generate inside it is the validator keys themselves, plus the slashing protection database. And sort of it makes you communicate then, of course, in a secure manner with the rest of your node stack. Yes, and the underlying hardware technology we're using here currently is Intel SGX. But then, of course, initial question that arises is, what is secure about hardware enclaves anyways, right? Intel is a centralized entity. The tool we use here, or the functionality we use here is proprietary, it's closed source, it's been subject to vulnerabilities in the past. So the memes are obviously bad. But then if you look around a little bit in the blockchain space, you realize like that teams like Flashbots, for example, heavily lean into SGX for their encrypted mempools in Suave, for example. We see block builders being run inside SGX hardware enclaves. We see liquid restaking pools like Puffer sort of using trusted hardware to lower the trust assumptions in node operators. Plus, we see it in ZK land, for example, with multi-proving and multi-verifying systems opting for SGX as the technology. So at the end of the day, it seems to boil down to like trust assumptions of users and sort of the teams developing this. And obviously, from a staking perspective, it boils down to your subjective threat model. So if we were to make an argument for why we should would want to validate from hardware enclaves, we could think of them as a simply purely additive ring of defense, like an additional layer to secure our signing keys. Moreover, trusted hardware is widely available, right? Everybody from us can get a hand on it if we wanted to, despite the fact that Intel has sort of deprecated SGX from the consumer products lines 2 years ago. On the server side, it's still widely available. And last but not least, using remote signing software in a diverse manner. So we increase our option space and sort of make our network potentially more robust in a sense. And very specifically, like node runners, what specific risks that node runners can sort of mitigate and potential benefits for them look like could be as follows, right? As you generate a key inside a hardware enclave, it only ever exists once within a unique enclave. So it's not possible to accidentally equivocate or double sign, particularly for home stakers or keys protected not in data centers. It's interesting that like as you're protected against hardware wallet theft, like the mechanisms in place there also apply to keys stored within SGX enclaves in this case. Think of a critical consensus client bug, introducing like potentially faulty slashing rules. Like as you run untemperable slashing rules inside a hardware enclave, you are immune to such failures. And last but not least, you avoid any sort of slashing risks as a consequence of a potentially compromised node or a client accessing this node, right? So you're immune to kernel level malwares, for example, operating system 0 days, rogue staking provider or cloud provider employee scenarios, etc. And what's pretty cool about it, it's solo staker friendly, right? You don't have to be an at-scale operator to use this technology. So that's basically what I did, what I wanted to test. So I got myself this slightly outdated piece of hardware, which is a NUC, right? SGX compatible. And for the sake of the demonstration, I wanted to run the whole client stack on this underpowered device. So I tested this on Ephemery testnet. Ephemery testnet is this neat little short-lived validator testnet, which basically allows you or has very low hardware requirements. Since it resets every week, so there's not a lot of block history or state history. So yeah, it fit nicely in my testing environment. And then of course I use some Docker Compose script to sort of run my execution client, consensus client, and validator client, and sort of the secure signer, my client interface on the untrusted side of my NUC. And then from there instantiated sort of secure signer, the tool, inside the SGX enclave, generated my key pair inside it, generated my deposit data file inside it, generated my voluntary exit message inside it, and made it securely communicate with the rest of my node stack. And right, so no staking gathering without looking at logs. So what you can see here is basically the secure signer log file telling us that, or showing the log that we successfully attested on Ephemery testnet at a given slot in a given epoch with a key stored and generated inside trusted hardware, inside a hardware enclave. So ta-da, right? It works when mainnet. Will still take some time. So Secure Signer, the tool, is still has recently been released, right? It's still in alpha. Codebase is still being worked on. It needs review. It needs audits. There are some UI and UX improvements we need. Feel free to get involved if you want to. What would also be nice is to get hardware vendor diversity, right? We don't want to rely on Intel, so it would be great to have AMD support at some point in time, or I know that there's work to enable support for AWS Nitro, for example. And then in terms of an outlook, the usage of Secure Signer is complementary with DVT. So as you can guess, you don't only have to necessarily have to store a full key inside a secure enclave, but you can store fractions of a key in it as well. So if you think back to the original diagram, we can sort of think of adding or running or validating from hardware enclaves being like an additional layer even around distributed key systems. Yeah, that's pretty much it. That's the long form read of my experiences testing these systems. It's also included as a step-by-step guide on how to set up the testing environment I just showed you. Yeah, don't worry, you don't have to necessarily own or have SGX compatible hardware at hand to test this, right? You, in a dummy mode, sort of Secure Signer can run on as a pure Rust app in your setup as well. So feel free to test it out, and yeah, shoot me a message if you want, and happy to take questions.
Thank you so much, Ladislaus.
Hi, thank you. 2 questions. One is that, is it the same as HSM? And the second question is, you mentioned the network which gets reset every week. What was the name again?
Okay, second question. It's called Ephemery testnet, and this is a public Ethereum testnet. There will be a talk by Mario later this afternoon, so I suggest you to stick around. And the first question was whether this is an HSM. So HSM stands for Hardware Security Module, I guess, which is, as far as I know, again, disclaimer, I'm not a computer security researcher, but the hardware enclave or secure enclave, but not smart, right? So you only store your keys at rest in hardware secure modules, as far as I guess. So Intel SGX is basically this technology with widens, in very simple terms, sort of widens the functionality to run program logic also inside a secure enclave, right? So it's not just about data storage; it's about trusted execution.
Any other questions? No? Okay. Well, thank you very much, Ladislaus.
Appreciate it. Thank you.